Okay, so yeah, thanks, Ursula, for a great introduction on this thrust of services and applications. So I'm Morley Mao. I'm from University of Michigan. So I'll be talking about some of the ongoing work in my group and also what we are planning to do in this institute, hopefully in collaboration with many people here. Some of the work we're looking at essentially is thinking about what are the security challenges that we need to address in this AI-based network application services, right? So essentially, we will have AI techniques deployed for a wide variety of network services and applications. But we know these services and applications operate in very complex, untrusted environments. And participants can be adversarial, as Miroslav illustrated. They can inject spoofed sensor data, and the early discussion of secure federated learning alluded to these models can be polluted by individual participants in this federated training system. So machine learning models themselves can be subject to a wide variety of attacks, for example, either white box or black box based attacks. And we also know that these network systems and applications, by design, they will adapt to resource variabilities. And that itself actually creates a new challenge because there's uncertainty in terms of how we can predict the system behavior. This lack of predictability is also very difficult, given that you want the system to adapt. But however, attackers could take advantage of this adaptation behavior to perturb the system such that it can lead to maybe unsafe driving behavior in the case of autonomous vehicles. So our goal in this part of the work is try to develop robust and attack resilient machine learning methods that can support a wide variety of network-based services and applications. So we want to do both bottom-up as well as top-down approach to understand design principles and by looking at specific examples. So I want to just highlight a couple of these directions that my group has taken on. Some of these are in collaboration with people in the institute already. As Miroslav alluded to, that we have started collaborating, looking at how do we improve the robustness of perception for autonomous vehicle driving systems, right? So we have published a paper which demonstrated that these attacks, LiDAR spoofing attacks, is possible from end-to-end machine learning data processing pipeline, and we're looking at defense solutions. Another project I want to highlight is this secure edge assisted multi-vehicle perception system. Essentially, we're looking at collaborative sensing, so which means that there will be individual entities involved in this distributed system sharing data, but the goal is to ensure that the end result is trustworthy and robust. Some of these later work, which we recently have been working on, is really developing a methodology to evaluate the adversarial robustness of various systems, machine learning systems, including, for example, trajectory prediction, dealing with out of distribution corruptions, and in semantic segmentation models where you can have trade-offs between large receptive fields and the corresponding robustness to attacks such as adversarial patch-based attacks. So this picture probably is very obvious, but I still want to illustrate that although so far our focus area has been on autonomous driving systems, but any kind of network system which rely on complex data processing pipeline, which leverages machine learning techniques, is our focus area, right? So any application, network application systems which use various machine learning modules as part of these data processing pipeline is of interest. And what's interesting here is that when you have some error, for example, the perception error, it will propagate and eventually will impact the control decisions in this case, right? So we are looking at essentially a system perspective of the end-to-end safety, robustness, security guarantees of the resulting end products when we have machine learning techniques implemented and deployed. So this is a slide taken from the Usenix security paper we have published last year. Essentially, this is trying to illustrate that we have some physical invariant property to defend against LiDAR-based spoofing attack. So we define this concept called free space. Essentially, And the LiDAR spoofing attack is to try to create these fake objects. And as a result of these fake objects, maybe it can lead to, vehicles suddenly break, lead to unsafe driving conditions. We have also started working on removing objects. And this is slightly harder than creating new objects. So free space is about when you have a essentially something called intra-occlusion or inter-occlusion patterns. There is just limited free space inside any valid vehicle's bounding box, right? Because you are blocked by a real physical object. So if attacker tries to spoof an object that doesn't physically exist, what we observe is that the lasers actually can penetrate through the spoofed vehicle. So you will have some violation of this physical invariant based on the free space concept. So you can detect that you see a large portion of free space inside the fake vehicle's bounding box, which essentially is a form of anomalies. So I just want to highlight this is a kind of example physical invariant property that could be hugely useful for when we apply machine learning techniques in real physical systems. For example, any kind of cyber physical systems, we can leverage these kind of insights that humans tend to have to improve the machine learning models. So just switch topic a little bit. As I mentioned earlier, we're working on this collaborative sensing systems for safer CAV connected automated vehicle driving. Here we are taking advantage essentially of sharing of data from presumably trustworthy other vehicles in the surrounding environment. And we're leveraging the edge computing support to be able to process the data and generate useful results. So the challenge obviously is that we have to ensure the communication latency is sufficiently low to generate the results that are meeting the real-time requirements. So we have developed a prototype. So far, we have ignored this trustworthiness assumption. Like we assumed everything is trustworthy. So we have ignored potentially individual entities could be adversarial. We have been able to develop a prototype system, which is published in the upcoming MobiCom conference, designing this multi-vehicle perception support. But however, as we mentioned before, this lack of trustworthiness is a huge challenge for us. How do we ensure, various techniques such as ground removal, partitioning, compression, which is to optimize minimal data exchange, can still have some kind of redundancy to detect potential misbehavior of the individual entities participating in this system. So obviously, this kind of sharing data is hugely helpful for example, blind spot detection. In situations like this, we can see like a hidden object that is blocked by another car. So for example, this car would be able to see the pedestrian crossing the road or another car changing lane. So generally speaking, this is very helpful for improving the safety of vehicle driving transportation system. Another direction we've been looking at is essentially this concept of understanding if an adversarial behavior of another vehicle try to just modify its trajectory. So without attack, what happens is this car is driving straight, but with attack, this attacker is trying to craft some history of its driving behavior, leading to this ego vehicle, the AV, falsely predict that this vehicle is going to deviate onto its lane, right? So this, as a result of this misprediction, it could take a hard brake, cause rear end collision. So essentially, we're doing various kind of testing, understanding adversarial conditions for models such as used for trajectory prediction, and we have found that they could lead to errors that are significant enough, like up to 10 meters, for the realistic attack scenarios. So this is some ongoing work we have been looking at. So I just want to summarize. There are a couple of obvious next steps we are working on in terms of assuming the vehicles are not trustworthy, what happens in this collaborative sensing environment. In general, we are looking for ways to design system principles to integrate secure, robust machine learning techniques to support mobile and system networks. And we're very excited about working with other team members of the Institute to realize this high-level goal. And with that, I think I'm done with this talk. Thank you.